Let's consider first how many distinct groups of protons and carbons a couple of example molecules have, and how that affects the appearance of their NMR spectra, both proton and carbon. It'll help us to begin to get an understanding of the connections between molecular structure and NMR spectra, which is of course the reason we take NMR spectra, so we can begin to understand and figure out chemical structures. We begin with one key idea. Protons on the same carbon will form one distinct group, whether it's one proton, two protons, or three protons on a carbon. There are exceptions, and we will consider them carefully later, but for now, treasure this notion, hold it in your heart, and don't let it go. Protons on the same carbon will form one group. So now, consider this molecule. It's the one we use as our standard in our instrument, methyl ethyl ketone. If I hold it up over here, it looks fairly distinct. Sometimes it's a good idea to be able to look at these things in the classic organic chemistry structure. Sometimes you just really want to be able to look at the classic molecular model. So that's what we have here. Now, this particular molecule features 1, 2, 3, 4, 5, 6, 7, 8 hydrogens in it. There are 8 protons in this molecule, but these 3 are attached to one carbon and are going to form one distinct group. These 2 are attached to one carbon. They're going to form one distinct group. This carbon has no protons attached to it. This carbon over here has 3 other hydrogens on it. They're going to form one distinct group. Together then we have 1, 2, 3 groups of protons in this molecule. And if we look at the proton NMR spectrum of this thing, sure enough we see 3 distinct resonances from it. It's interesting, methyl ethyl ketone, the commercial grade stuff we use when we make our standard, is actually contaminated with a trace of acetone. That's the way it comes when they sell it. And so we do see a 4th peak in there. It's very common to have contaminants trace other materials in our NMR spectra. It's something we just have to get used to from time to time. But it does show the 3 resonances we would have expected to see. If we look at the carbon spectrum for this molecule, we would expect to see 1, 2, 3, 4 carbons, and indeed the spectrum reveals 4 distinct carbons in the carbon NMR spectrum for this thing. And so exactly what we would expected to see, and it makes a nice correlation between what we see in our spectra and the molecular structure. It is diethyl ketone. Classic organic structure reveals that it is a larger molecule than methyl ethyl ketone. It has 10 individual protons in it. But if we look at the molecule molecular model here, it does reveal something kind of interesting. It's a little bit different than methyl ethyl ketone. There are the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 protons in here, but they are 3 on this carbon, 2 here, 3 there. 4 distinct groups. But there's one other factor. This molecule, look at it carefully, is beautifully symmetric. There's a mirror plane right down the center of this thing. Therefore, it's going to render the right side and the left side of this molecule identical to each other. That's going to have the effect of taking these 2 carbons and the protons attached to them and forming one group out of them, not 2, because they are on opposite sides of a mirror plane. These 2 carbons and the 4 protons attached to them will also form one distinct group. And so while it's a larger molecule than methyl ethyl ketone, it actually only is going to show 2 distinct groups in its proton NMR spectrum, and indeed that is exactly what we see. Larger molecule, but a simpler spectrum. Symmetry can play a big role in this interpretation of spectra and understanding the connections between spectra and the molecular structure that we're trying to solve. Looking at it from this perspective of the carbons, once again, there are 5 carbons in this molecule, more than in methyl ethyl ketone, but the same symmetry that we looked at for the protons works here as well. These 2 carbons will be equivalent to each other. These 2 carbons are equivalent to each other, and then in the middle, the 1 carbonyl carbon that forms a 3rd distinct group. Therefore, when we look at the carbon NMR spectrum of this molecule, we would expect to see, and indeed we do see, 3 distinct resonances here. Together, these 2 fairly simple example molecules nicely illustrate the connection between the number of groups distinct groups that a molecule will feature, how molecular symmetry can drastically change the expected number of groups, and how each group, distinct group, proton or carbon, will form a distinct resonance that we can see in our NMR spectra.